Pre-Cal, Chapter 2.5, Transformations. All right, we're going to talk about the different transformations that happen on functions that affect their graphs. Vertical shifts, you will add or subtract on the outside of the function. Horizontal shifts, it'll happen inside of the function. You always flip the sign of h and leave the sign of k. So here, use the graph of f of x equals x squared to graph x squared minus 4. So this is our parent function. So I'm going to graph my parent function to start with. You can get values for your parent function on your calculator or on Desmos. If you type it into y equals, we have x squared, and then look at my table. You can find your values there. I have the point 0, 0, negative 1 and 1, 1, 2 and negative 2, 4. This is my parent function, which is y equals x squared. This minus 4 out here is a vertical shift. It's outside of our squared of our function that's happening here. So that means we are going, this is k equals negative 4, which means we're going down 4 places. So we can take each of these points and just shift them down 4, or you can look at your table here and get your values that way. The next one, graphing in stages, we have two different things that are going on. We have this inside our function, which is horizontal, and this outside our function, which is vertical. You always flip the sign of the horizontal. So we have h equals negative 3, which means we are going left 3. And we have k equals negative 5. You always leave that sign of k, which means we're going down 5. So graph in stages, I'm going to start by graphing my parent function, which I graphed just a second ago. And you can get these values on your calculator under the table feature. You have the point negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. So this is x squared. I'm going to start with my x plus 3 squared, so without the vertical shift. That means I'm taking each of these points and I'm shifting them left 3 places. You can also plug this into your calculator, x plus 3 squared. Look at your graph that way, and then look at your table. So this one is x plus 3 squared. We have the point negative 5, 4, negative 4, 1, negative 3, 0, negative 2, 1, and negative 1, 4. Remember, you can always pause these videos and restart them. And then I'm going to do the f of x function, which is this, and then down 5. So basically what I'm doing is shifting all of these points down 5. And I can look at this on my calculator this way. And then look at my table. So now I have negative 5, negative 1, negative 4, negative 4, negative 3, negative 5, negative 2, negative 4, and negative 1, negative 1. So this is our f of x, which is x plus 3 squared minus 5. When it comes to reflections, if you have the negative on the outside of the function, it reflects into the x-axis, so with respect to the x-axis. And if it's on the inside, it reflects with respect to the y-axis. Compressions and stretches, if your coefficient is on the outside of the function, Anything between 0 and 1 is a vertical compression. It's going to smush it down. And this is the absolute value of A here because of the reflection. And anything where the absolute value of A is greater than 1 is going to stretch it out. If it's on the inside of the function, if A is greater than 1, it's a horizontal compression. It's going to compress it this direction. And if A is between 0 and 1, it's going to stretch it out this way. So we're going to use the graph. 2 times f of x. So what we're doing is we're multiplying our y value by 2. So essentially when you take this, you multiply your y value by 2 each time. So this one, your y value is 0, so it's going to stay 0. 0 times anything is 0. Your first notch here, your y value is 1. 1 times 2 is 2. So now it's growing. Here at pi, we're still at 0 because 0 times 2 is still 0. At the next one, we're at -1. -1 times 2 is -2. So we're stretching this direction. At 2 pi, we're still at 0. And at 3 pi, we're still at 0. Here we're at 2. So this has stretched it. Vertically. On the inside, so this one we had A is greater than 1, which means it's a vertical stretch, which is what we have done here. Here we have A again is greater than 1, but it's on the inside, so this is going to give us a horizontal compression. So what we're doing now is we're multiplying our x value by 2. When we plug this in, we still have our 0, 0 point, but now it's happening twice. So this means it happens twice within the same amount of time that it happened once before. So we're kind of smooshing everything over. So if we have our pi, 2 pi, 3 pi, I hope that you recognize this function as the sine function. Instead of it being 0 here, it's now 0 at half of that. And it's going to be like that the whole time. Our new maximum point there is in between those two values. This is what it's going to look like. And you can verify this by typing it into your calculator with sine and cosine. You need to be in radians mode. This one would be the sine of x, and then this one would be the sine of 2x. And you can look, there's the sine of x. Now my notches are different here. My notches are 1 instead of pi over 2. And see that it happens twice. Writing the new function, if we're going left 2 units, that means that h is going to equal -2. And when you plug that into your equation, we're using the function absolute value of x. When you plug that into your equation, you have to flip the sign of h. So what we've got here is y equals a times x minus h plus k, like that. So if h is -2, then we have y equals x plus 2 inside our absolute value. If we're going up 3, that means that k equals +3. So what we have is y equals the absolute value of x and then plus 3 on the outside. Reflect into the y-axis. If we look back up, then that means our negative goes inside our function. So we have y equals the absolute value of -x. The next one, combining graphing procedures. So here we've got a rational function. The parent function here would be 1 over x. So this would be our a value because 3 is not 1, so 3 would be a. 3 times 1 is 3. This would be our h value. And this would be our k value. K is on the outside of the function, A is on the inside, or H is on the inside. So what we've got here, I'm going to start with my parent function. I'm going to kind of graph in stages here. I'm going to have 4 graphs. Y equals 1 over x, which is my parent function. For 1 over x, if I'm at 1, 1 over 1 is 1. If I'm at 2, 1 over 2 is 1/2. If I'm at 1/2, 1 over 1/2 is 2. And you can get these points on your graph. A rational function has asymptotes here. Over here, if I'm at -1, 1 over -1 is -1. I'm at -2, 1 over -2 is -1/2. I'm at -1/2, I'm down at -2. This is our parent function. You can totally get this on Desmos or on your calculator. Now I'm going to do my stretch first. So I'm going to say y equals 3 over x. My stretch, I'm going to put this in my calculator so you guys can see it. 3 over x. Look at my table. At -1, I'm at -3. And at 1, I'm at 3. At 2, I'm at 1/2. 1.5, I'm sorry. And at -2, I'm at -1.5. And when I look at my graph, I've got the asymptotes going. It's just a little bit of a stretch there. So now if I do with my h value, which means I'm going right to, so A was a stretch, a vertical stretch. H means I'm going right to, because I flipped that sign, so that means h equals +2, which means I'm going right to. So now if I plug in 3 over x minus 2, oops, sorry. And I graph that. Now notice I've shifted right to. So instead of my asymptote being at the at the y-axis, my asymptote is now going to be at x equals 2. So this is 3 over x minus 2. I'm going to look at my table to get some points. I have the point 1, -3. And I have the point -1, -1. I have the point 3, 3, 3, +3. And I have the point 5, 1. And then the last one, this +1, means we're going to go up 1. So my f of x here is what I'm graphing now, which is my what's given to me function. I know I'm right 2. So now instead of my asymptote being at the x-axis, it's going to be up 1. And so I'm taking these points and I'm essentially shifting them up 1. So to do that on my calculator, 3 over x minus 2 plus 1. Look at my graph, notice that it's shifted up. Look at my table, find some values. I've got the point of -1, 0. I'm at the point 1, -2. I'm at the point 3, 4. And I'm at the point 5, 2. So that's just graphing it in stages, looking at what each little thing does to it. You do not always have to graph it in stages like this. And then the last one, I have the function the square root of 1 minus x plus 2. So I'm going to rearrange this a little bit because my equation is going to be y equals the square root of a times x minus h, and then plus k. So I'm gonna rearrange it a little bit so that my x is in the front. So what I've got here is f of x equals the square root of negative x plus 1 plus 2. I'm gonna pull my a out front because it's a negative here. I'm just gonna negate each piece. So I have negative x minus 1 plus 2 like this. This negative reflects with respect to the y-axis. This is an h equals positive 1 because we flipped that sign of h there, which means we are going right 1. And this is a k equals 2, which means we're going up 2. So I'm going to graph this equation. My parent equation is y equals the square root of x. So y equals the square root of x. You have the point 0, 0, 1, 1, 4, 2, and 9, 3. That's my parent function. So if I do the negative square root of x, which is what I'm going to do next. So if I have the negative square root of x, excuse me, it reflects with respect to the y-axis. So everything is flipped over. I have 0, 0. I have negative 1, 1 this time. I have negative 4, 2 this time. And negative 9, 3. Now if I have the square root of negative x minus 1, I'm shifting to the right 1 place. So each of these points is going right 1. It's kind of hard to differentiate on this graph. Square root of negative x minus 1. And the last one is that in up 2 places. So I'm taking each of these and I'm just shifting up 2 places. And that's going to give me my final graph, which is f of x. And that's it.